Welcome to Study Loop.
We have a stone that's suspended from a wire that is wrapped around a outer rim of a pulley here. The pulley has is a uniform disc that has mass of 10 kilograms and a radius of 50 centimeters. And we say that the stone travels 12.6 meters down. I'm going to measure y being up. In the first 3 seconds starting from rest. And we want to find the mass of the stone and the tension in the wire. So we have the mass moment of inertia of the pulley is given by this expression. We know we're basically assuming that this thing is falling, again, without air resistance or anything. So it's falling with a constant acceleration because of the force of gravity. Now, we know that it falls 12.6 meters in 3 seconds. So we can figure out that we know that the change in position is 1/2 the constant. If the acceleration is constant, we know the change in position is 1/2 a delta t squared. And again, if we measure 0 from where the stone started and it had zero initial velocity, then this is the expression. And we can figure out that a is 2 times delta y divided by delta t squared, and that comes out to be minus 2.8 meters per second squared. So the stone is falling. We can draw free body diagrams of the stone, and that says that the tension minus the weight of the stone must equal the mass of the stone times its acceleration. And we can draw a free body diagram of the pulley here. And well, we have these reaction forces here that just counteract the weight of the pulley and the tension here. But that's not going to give us any information. We're just going to take moments about the center here so that these two forces drop out. And that gives us that any applied torque that we'd have minus T times R, this is the radius R, must be equal to J, the mass moment of inertia of the pulley, times its angular acceleration. Now, we know the angular acceleration is simply the acceleration of this block, or this stone, divided by R. We're assuming that there's no applied torque here. They didn't specifically say it, but they didn't say that there was, so I'm going to assume that there wasn't. Or that there was, and then somehow it got released. We can then do some, we can solve for some things. We can solve for T from here, since this is 0. And we get T equals minus the mass of the pulley, or minus 1/2 times the mass of the pulley times the acceleration. We have the acceleration here, and we know the mass of the pulley, so we can find that T equals 14 newtons. And then we can find the mass of the stone from this expression here. Since we know A, we know G, and now we know T, and it turns out the mass of the stone is 2 kilograms.